So hello friends, I'm up with a new video on the chapter Electrochemistry. So let's start with the topic. So what actually electrochemistry means? Now electrochemistry composes of two things. The first thing is converting of chemical energy to electrical energy, which is done by a cell known as electrochemical cell. And the next one is electrical energy to a chemical energy, which is done by electrolytic cell. Okay, these two things compose electrochemistry. It is a branch of chemistry which deals with chemical energy to electrical energy to chemical energy. So first let us learn what is it about the electrochemical cell. Now electrochemical cell is also, let's take an example. In the sense, one type of electrochemical cell, that is galvanic cell, which is also known as voltaic cell, the galvanic cell or the voltaic cell. Now one of the example of galvanic cell is Daniell cell. So let us look at the figure, what actually Daniell cell composes of. So let's take two beakers kind, and we'll have a salt bridge in middle, which is what is salt bridge. Now salt bridge is something, see, if we have a normal beaker, we'll have a beaker and two electrodes in it, right, and it will be connected to the circuit. Now generally this is the thing, but let's take two beakers in which in each beaker we have one electrode. Okay, now if we have it in that sense, now if it is this beaker, then we directly connect it to the circuit because both the electrodes are in the same beaker. Now here we have two beakers in which each electrode is placed in different beakers. So for connecting this, we need a salt bridge. So what is a salt bridge made up of? Salt bridge is made up of agar-agar gel. It is actually saturated with KCl or KNO3. Okay. Now, this is the figure. This is the, this is how the experiment or the experiment is placed. Okay. Now let us take ZnSO4 in one beaker and CuSO4 in one beaker, and this electrode is made up of copper, this electrode is made up of zinc, and this is how the Daniell cell is worked. And now let's look at the cells. Okay, first let us start with anode. Okay, now that is this part. This part is the anode part and this part is the cathode part. Now anode half cell. See, it's because we are separating these two into each two different beakers, we call it as half cell. Anode half cell. Now, one easy way to learn this is lone. So, what is lone? Lone, L is left, O is oxidation, A is anode, N is negative electrode. So, what is actually anode? Left, oxidation, anode, negative electrode. So, just remember, anode is lone. Anode, lone. So what is anode? Left oxidation, anode, negative electrode. Okay. Now the equation at the left half cell is this for the zinc. Okay. It's where it is oxidation. What is oxidation? Removal of electrons or addition of oxygen is called as oxidation, right? Now here the electrons are being removed out. And now let's look at the cathode half cell. So what actually happens in cathode half cell? It's just the opposite of the anode, that is here oxidation. So here it will be reduction. So what is reduction? Addition of hydrogen atoms or electrons and removal of oxygen atoms, right? So when you add electrons here, so here you're adding electrons and you're making a complete atom. Now the overall reaction. So let's combine this left anode reaction and this right cathode reaction to make the overall reaction, which we get in this form. Fine. Zn plus Cu plus 2 gives rise to Zn plus 2 plus Cu. When you combine two equations or when you add two equations, if the opposite things are same. Now here this and this, they are in opposite places and they are same. So this get cancelled. So we get the complete equation in this way. This is a very important chapter, and here it's more than conceptual. It should be a problematic chapter. It is a problematic chapter, so you should practice more problems on this chapter. So let's now see what is the cell notation of the half cell things. Okay, the anode half cell as we saw and the cathode half cell as we saw. So the anode should be placed in the left and the cathode should be placed on the right. And this is also a barrier between, like, this indicates the separation actually. This is the left and the right. And now, okay, there is a point, I mean there is a kind of trick kind of thing. Now here, lower electrode potential, that is anode. Anodes will have lower electrode potential. Whatever element you keep at the anode, or either zinc or any other thing, see, anode, they will have lower electrode potential. Okay, that will be higher negative value. Lower electrode potential in the sense the negative value will be higher. Now higher electrode potential is cathode, which will have a higher positive value. So that is higher electrode potential. See. Now let's take an example and I'll show you how the formula works. That it's given that this potential is, this has an electrode, zinc has an electrode potential of 0.76 and copper has an electron potential of 0.34. As I have told you, anodes will have lower electrode potential and cathodes will have a higher electrode potential. See, now how the formula, what is the formula and how it works is, the E naught of the cell is E cathode minus E anode. Now what is E cathode here? This is E cathode and this is E anode, right? Now you subtract this from this and you should consider negative here. So it's E cathode minus E anode. Now cathode is what? It's on the right side. Now anode is what? It's on the left side. So it's E right minus E left. It's just for easy remembrance, and here is the calculation for this. As you substitute these values and you just calculate that. Okay. And next let's enter the electrode potential. Electrode potential. What is electrode potential? The potential difference between electrode and its ion is called as electrode potential. What is electrode potential? The potential difference between the electrode and its ion. What is the electrode? Electrode is what we saw here. See, this is electrode. And what is its ion? Ion is copper ion, right? That's what I'm talking about. What the potential difference between the electrode and its ion is called as the electrode potential. Now the electrode potential is of two types. Now one is oxidation potential and the other one is reduction potential. Oxidation potential is the negative of reduction potential. Reduction potential is the negative of oxidation potential. Is just the negative signs that are different, but magnitude wise they are the same. Okay, next let's enter the next thing, that is standard electrode potential, E naught. Now what is standard electrode potential? The potential developed here is called the standard electrode potential. What is the situation here? Where you have 1 molar concentration of the ions at 1 atmosphere at 298 Kelvin. 1 molar concentration of the ions and 1 atmosphere 298 Kelvin is the potential developed here is called as the standard electrode potential. Okay, at this situation, whatever the potential which is developed, it is called as the standard electrode potential. And now let's see the next point. According to IUPAC, that is SEP is equal to SRP. Standard electrode potential is equal to standard reduction potential. What is reduction potential? As we have seen before, that is, reduction potential is negative of oxidation potential and oxidation potential is negative of reduction potential. And now let us see the next thing, standard hydrogen electrode. Now what is She here? She is standard hydrogen electrode. It is actually taken as the basic electrode. So it's just for an easy understanding that we consider the hydrogen electrode. Okay. Now the oxidation part. What is the oxidation part? That is the anode part and this is the cathode part, right? Oxidation, what is oxidation? Removal of electrons, and reduction is the addition of electrons. Now this is the standard value. You should remember it perfectly. Now what is the E naught of H? As this is standard hydrogen, that is She. Now this is the basic thing which we should remember. So this also is the standard value. For H plus H2, it is 0.00 volt. See, using She, we can find out standard electrode potential of single rod. Now, as we have seen an example here, that is zinc and copper, right? We have seen an example here, zinc and copper, as we have got the reduction potentials of this zinc and copper as minus 0.76 as for zinc and 0.34 for copper. How do we get it? Like, we just can't get it. We don't know it from the beginning, right? As from where the experiment started, we just took the hydrogen as a basic and an ideal electrode. With the help of the hydrogen, with the help of the standard hydrogen electrode, we could find out the other elements reduction potential. Okay. So that's what the use of this is. Using She, we can find out standard electrode potential of a single rod of any other element. Okay. Now we have something called as activity series, which is also called as electrochemical series. Now first thing which comes in the activity series is lithium. Lithium, Li plus Li, which has the highest negative. Okay, in the whole of electrochemical series, this has the highest negative, that is minus 3.05 volts. That is minus 3.05 volts. And the least negative or the highest positive, we can say, is F2 and F minus. This is highly reducing agent, as you know. Fluorine is the most highly reducing agent in the periodic table. Now it's highly positive. This is plus 2.87 volts. Okay, we have seen that as anode will have highly negative value and cathodes do have highly positive value. And this is the activity series. So you should remember, there's no need to remember it, but just remember the first one and the last one, that is the lithium and the fluorine part. Okay. Now we go for the application. Okay, here in this part, see, you can see hydrogen, right? Below hydrogen everything will have negative, and above hydrogen everything is positive, and this will have the highest positive, and below hydrogen is the negative part, and this has the least negative. You know, right? Negative, if the number of the negative is increasing, it becomes least value. The value becomes lower. Okay, it has the highest negative value. Now we go through the applications of electrochemical activity series. Electrochemical or activity series. Electrochemical series or activity series. Now, relative strength of oxidant or reductant. What are the applications? Like, how is electrochemical series useful for us? Is relative strength of oxidant or reductant. Now, if we see higher negative SRP, who has the higher negative SRP? Lithium, right? It is the strong reductant. Oh, sorry, I just told you that fluorine is the most reducing agent. I'm sorry, it's oxidizing agent. Lithium is the most reducing agent. And next, higher negative SRP is stronger reductant, and higher positive SRP is stronger oxidant. Okay. Now, to calculate EMF of the cell. Now, we have 3 uses of electrochemical series. Okay, there are totally of 3 uses. Now, first thing is relative strength of we can compare which element is most reducing, which element is most oxidizing with the help of the first application, that is relative strength of oxidant and reductant. And then now the second application is to calculate EMF of the cell, and the third point is reactivity with dilute HCl. Now see, second application to calculate EMF of a cell. Now, how is EMF of a cell calculated? We have seen a formula before that EMF of a cell is EC minus EA. What is EC? E cathode. EA is E anode. EMF should be, if it is spontaneous reaction, if it is a spontaneous reaction, as you know, delta G will be negative. if it is a spontaneous reaction. Now EMF should be positive if it is a spontaneous reaction. And what is EMF? How is EMF of a cell calculated? That is E cathode minus E anode. And next, let us see the third application, that is reactivity with dilute HCl. How does this work? Now, as you know, the basic sheet thing is E0 is 0 volts. The more the negative than H2, liberate H2 gas, meaning to say in electrochemical series, as you have seen, H2 is here, and below the H2 till lithium we have negative values. The more negative, the more it liberates H2 gas. Do you get it? The more the negative, the more it liberates H2 gas. Now let's go into Nornest equation. Nornest is a scientist. Now what a chemist. Nornest equation, concentration other than 1 m concentration, 1 molar concentration. Till now, whatever we have seen, that is for 1 molar concentration. You remember we had seen that standard reduction potential. What is standard reduction potential at 1 molar concentration? 1 atmosphere, 218 Kelvin, right? We have seen it right here. See, 1 molar concentration of ions, 1 atmosphere, 298 Kelvin. That is standard reduction potential. Okay, that is standard reduction potential. Now we are talking about a situation where it's not 1 molar concentration and it's any other concentration other than 1 molar concentration other than 1 molar concentration, and this equation is given by Nornest. Now what was the equation which we followed under SRP? Was this, right? Now let us see the Nornest equation. For a single electrode, as we have taken the 2 beakers and we have put single electrodes, right? In the same way, for the single electrodes, E is E0, the standard reduction potential E0, minus 0.059 by N log of products by reactants. This is the Nornest equation. You should remember this. What is it? E is equal to, what is the the formula for that? E is equal to E0 minus 0.0591 by N log products by reactants. This is very important. Remember this. Now let's move on. There is another formula in the same way. If we calculate this, we get 0.0591 by N. If we calculate this without calculation of this, if they give in the question, if they give different temperature, or if they tell us to consider R as something else except the gas constant, except that value, if they tell us to consider something else, then we can use this formula, that is E is equal to epsilon naught minus 2.303 RT by NF log products by reactants. Okay, remember this formula too. Now, okay, in Nornest equation, we have another relation also. So you remember the Nornest equation now perfectly. Now let's move on to another relation for the Nornest equation. E cell is E0 cell minus 0.0591 by N log QC. Now what is log QC? I hope you have learned the chemical equilibrium part of the 11th class. Now what is log QC? Now if we have an equation, x plus y gives rise to xy, this equation, now at equilibrium we calculate Kc, right? At equilibrium we calculate Kc. What is it? xy by x and y, the concentration of xy by xy, right? Now except the equilibrium, let's have a, see, this is equilibrium and this is before equilibrium, and this is after equilibrium. Fine, this is before equilibrium and this is after equilibrium. Except equilibrium, any other situation, either before or after, we call it as QC. Fine, except the equilibrium. Now there will be three cases in this. Let's think this is QC and this is KC. There will be a between thing where this is QC or KC. There will be another thing, this is KC and this is QC. So there will be three cases. There are three cases of QC, KC and this. See, it is where the QC is more than KC. Here forward reaction will be taking place, forward reaction, and here it will be backward reaction, and this is called as equilibrium. Fine. Now, if they give in the question, if they ask us to calculate with the help of QC value, you should use this formula. It's just that here we are using log P by R, and it's just that except this we are substituting this value. It's the same thing here. See, QC also it's the same thing, like X, Y, X and Y. Fine. It's the same thing. There's nothing new in it. And at equilibrium, as you know, QC is equal to KC. E cell will become 0 at equilibrium. Okay. And if they ask us to calculate with the help of KC, we just substitute KC. This chapter is very important and you're supposed to practice many problems on this. Mostly the NCERT part of the problems would be helpful. The examples and the in-text questions and all. So let's move to Gibbs free energy. So what is Gibbs free energy? Delta G is minus NFE cell. Just remember this. Delta G is minus NFE cell. This is the Gibbs free energy formula. Delta G is equal to minus NFE cell. Now delta G naught is equal to minus NFE naught cell. Okay, delta G naught is equal to minus NFE naught cell. When you're taking delta G naught, you should take the E naught. When you're taking only delta G, you should take only E cell. Next one is delta RG. Then you should take RT ln K. When it is delta RG, you're supposed to take minus RT ln K. Don't forget about the minus. Okay. Now, Gibbs free energy. For the reaction to be spontaneous, if we say the reaction is spontaneous, then delta G should be negative, delta E should be positive. We have already talked about this, isn't it? Now let's move to electrolytic cell. So whatever we have seen till now, that's electrochemical cell. And now what we are going to see is electrolytic cell. You remember what is electrochemical cell? Converting chemical energy into electrical energy. And what we see now, that is electrolytic cell, is converting electrical energy into chemical energy. Fine. Now, what are the sign conventions that you have seen for electrochemical cell? That is electrochemical. See, electrochemical cell, the thing we have seen is lone for anode, right? Lone for anode. Here N is what? Negative. Now in electrolytic cell, anode becomes positive. The sign convention is opposite to electrochemical cell. Just remember this. This is a very smaller minor point which we actually miss. Sign convention is opposite to electrochemical cell in electrolytic cell. So anode becomes positive, cathode becomes negative. Earlier we have seen anode as negative and cathode as positive. Now, the chlorine electrons move here and the current is moving. See, current always goes in the opposite way to the electrons. So if the electrons are moving like this, then current will be like this. As you know, current is in the direction of protons and not in the electrons, right? Now, let's see next point. Flow of electrons is anode to cathode. See in the diagram, flow of electrons is anode to cathode, right? So the current is traveling in the reverse way. Anions move to anode, so chlorine ions is liberated and Na plus is deposited. Here we are taking an example of NaCl ion where anions move towards the anode. Anions generally move towards the anode, so chlorine is liberated and Na plus is deposited. So on this electrode, Na plus is deposited and chlorine electrons are liberated. This electrons travel towards the cathode and the current travels towards in this direction, as current is opposite to the electron flow. Okay, that is all about the electrolytic cell. That's just an opposite of electrochemical cell. There's nothing much to know about it. And next we go for Faraday's first law. So what is Faraday's first law? The charge is directly proportional to the mass of the substance deposited. The charge given to the cell is directly proportional to the mass of the substance deposited on the cell. On the electrode. Now, if you give more charge, more mass will be more mass will come and accumulate on the electrode. If you give less charge, less mass will come and accumulate on the electrode. M is what? Mass of the solute. Q is what? Quantity of electricity. And C is what? Electricity, nothing but the charge. The I is Q by T. Current, quantity of electricity. That is, current is the flow of charge, rate of flow of charge. Okay. Now, M is directly proportional to Q. Now, what is Q? C. We have M is directly proportional to Q. Now Q here is EQ. Okay, not this E, this EQ. This is the charge of the electron. What is the charge of the electron? 1.6 into 10 power minus 19 is the charge of the electron. Now M is directly proportional to capital Q. M is equal to small EQ. See, what we're just removing the directly proportionality constant here, and we are giving a small e here. Fine. Now what is Q? Q is CT. I've told you, right? So ECT. Q is CT. So it's ECT. Now E is electrochemical valent equivalent. Electrochemical equivalent. So this directly which we have taken, proportionality constant which we have taken here is E is electrochemical equivalent. This thing is this, sorry. Here Q is this, okay. This is just for one electron which I gave. Okay, fine. I just told you for an info. Now E is electrochemical equivalent. Now here M we have got ECT. Right? M we have got ECT. Now we can substitute this E with E by 96500. This is the Faraday's number. Now E by capital E by 96500. So let's substitute this here. M is capital E by 96500 CT. Fine. Now, we have another formula. M is equal to capital ACT by ZF. So, by comparing these two formulas, we get to know. Now, what is F here? F is the same number. Don't worry about the F. Now, from here we get to know. We can cancel this, this, and this, and this. So, here we are getting E is A by Z. Now, what is A? Atomic mass. What is Z? This is the charge. Fine. See, A is the atomic mass, Z is the charge. Now E is, we have seen here, E is 96, so E by F is small e. And what is E? E we have seen here A by Z. What is E? E is A by Z. So let's substitute. E is A by ZF. We get the small e as A by ZF. Okay, these are the formulas. Now, charge of 1 mole of electron, when you take 1 mole of electron, the charge on that is 96500 coulombs. That is 1 Faraday coulomb. Okay, 1 mole electron charge is equal to 1 Faraday. Remember this. Okay. Now let's move on to, that is the Faraday's first law. What is Faraday's first law? Faraday's first law is M is directly proportional to Q. Remember this, okay? And you can just you can just go on getting the formulas from this Q. Okay. Now what we'll go on to Faraday's second law. What is Faraday's second law? M1 by M2 is equal to E1 by E2. Okay. This is the mass of the solute. This is the mass of the ions deposited. This is the equivalent weight of the ions. Okay. These are just the examples. Don't think I'm skipping some topics here, because the things which I'm not explaining is just the examples which I have solved for a better understanding. Now, conductance in solutions. Now we have two types of things, okay, like as we know we have cells, two types cells, electrolytic cells and electrochemical cells. We have two types of conductors. So the first thing is electronic conductor and the second thing is electrolytic conductor. And the electronic conductor is, see, it's from now it's going to be very normal, it's going to be very easy. Electronic conductor is flow of electrons. As temperature increases, conductivity decreases. Just remember, electronic conductor, flow of electrons, electronic flow of electrons. And if temperature is increased, conductivity decreases. Electrolytic conductor is flow of ions, electrolytic ions. As temperature increases, conductivity increases. Next, see, in electrolytes we have two types. One is strong electrolytes and one is weak electrolytes. You have learned this in equilibrium again, and I'll teach you when I do this that chapter. And non-electrolytes are, for example, it's urea or glucose. There are many other non-electrolytes examples. Now let's come to the electricity part of the chapter. That is, first thing what we learn, and that is resistance. So what is this resistance all about? Resistance, you have learned it in physics too. Rho L by A. Rho is the specific resistance. This is particular for one type of material. This is very specific for each type of material. You take it for the zinc, it will be one type. You take it for copper, it will be one type. You take it for silver, it will be one type. So this value differs. It's a constant value. Now this length and area is changeable. Now this length by area, L by A, is called as G star. Now let's mark it as G star because we might get confused with the Gibbs energy, and you should follow it. G star, this is called as cell constant. L by A is G star, which is also called as cell constant. Now we can write R as rho G star, right? Isn't it easy? Yeah. Now let's come to conductance. So, see, resistance, we have rho L by A. Conductance is just the opposite of resistance. I mean, opposite in the sense is just a reciprocal of the resistance, right? So let's write the formula of resistance here. C is equal to 1 by rho L by A. Now when this goes up, it will become I.